So welcome back, everybody. The topic this week is a little bit more, how to say, more going through programs. And you should have received an email with a program, which is a kind of a more compact template for setting up a neural network code. And that code is structured in terms of classes. And I guess many of you are familiar with that. And it contains many of the ingredients which we have discussed before the winter break. So it contains an implementation of the stochastic gradient methods, the different schedulers for updating the learning rate, like ADA-grad, this adaptive momentum method called ADAM, the root mean square propagation, or just RMS-prop, and many other things. So it gives you a kind of input to how you can structure your own program for neural network. And I think this is something which is going to be useful for the second project. So actually to develop your own neural network code. Clearly, one of the things which we are going to do when we've gone through the basic structure here, discussed many of the technicalities, is to start looking at how to use a software like TensorFlow, which was released by Google. Alternatively, if you prefer to use PyTorch, which was released by Facebook, this is also an alternative to developing codes for deep learning. In particular, if you're thinking of convolutional neural network or recurrent neural network, or using autoencoders, variational autoencoders, or GANs, which are other methods which are widely popular in the literature and which move into the domain of unsupervised learning. And we're going to discuss these methods after we've done with today's lecture. So next week, we will begin with convolutional neural networks and recurrent neural networks. And in that case, we are not going to write our own code unless you guys want to. And we are going to then simply use an interface to TensorFlow, which is called Keras. And that's an API, which is very easy to use. And I will show you some demonstration of that today as well. So today is mainly going to be a going through a Jupyter notebook with the structure, the basic structure of the code. And as usual, you will find the lectures, the videos of the lectures, you will find them uploaded here. So like this, from January 31st, you will find the basic structure and the basics of the deep learning. So we went through last week the second part on automatic differentiation and the backpropagation algorithm. And now we are going to implement these algorithms. So let's switch immediately to the Jupyter notebook. So this is the lecture slides which we had last week. And we are basically going to use these. And one of the things which we discussed, so if we just scroll down here, it contains at the beginning a quick reminder of the backpropagation algorithm, the way we are implementing it for a neural network. Just to remind you of that, we have a feed-forward stage where we run through the network with the inputs and produce an output. And we have initialized the weights and the biases, which are the parameters of the model. And with those, we can then produce an output. And with the backpropagation algorithm, we train the network so that we get the optimal parameters through a gradient descent. So the backpropagation algorithm is just an algorithm which uses the chain rule, where we start with the derivative of the cost function at the final layer, which is the output layer. And then we go backward till the first hidden layer, and we produce this quantity delta J, which is an important quantity which is derived by using simply the chain rule for derivatives. And last week we saw how that linked with the reverse mode of automatic differentiation. And then we have the expressions for the gradients, for the weights, and the biases. And this parameter eta is the parameter which we call the learning parameter, or just the learning rate. And we discussed that in connection with gradient descent methods. And in the implementations which you're going to see first here, we are going to use a very brute force way of doing this. And we are simply going to play around with different learning rates. Now, in the program, which I sent you by mail, the way you do this is to use these schedulers like ADA, GRAD, root mean square propagation, or ADAM. These are methods which are highly cited and much used in the setup of a neural network and in the how to say the so I'm just missing the words now, actually the fitting of the learning rate when we do the iterative update of the weights and the biases. So we went through some of these things last week, but let me quickly remind you of some of the ingredients here. So the example which we have is an example which is tailored to a classification problem. So the simplest type of classification problem is the one which we encountered with logistic regression, where we use the cross entropy to define the cost function based on a maximum likelihood of the product of individual probabilities. And in that case, we would define a sigmoid function, which we then use for the probabilities of an output equal to 1, one output equal to 0, which is simply this number here, and 1 minus that number. And the parameters beta are then used through the, then optimized through the gradient descent or Newton-Raphson method. And in our case, we're also going to use the sigmoid function as an activation function. In the program which I sent you, which is much more flexible, you can play around with many different activation functions. So the program in the basic slides here is more meant as a kind of a pedagogical introduction. And then the other program is the one which may look more, which may be more similar to what you are going to write at the end. So the quantities which we wanted to look at now, the data set, is the so-called MNIST data, which is a data set which contains images of handwritten numbers from 0 to 9. So we have 10 classes corresponding to the 10 numbers. And then the function which we use is this so-called softmax function. And this softmax function looks very much like the original Boltzmann distribution. And it contains here a normalization factor, which is the sum over all the classes. So uppercase letter K stands for the different classes which we have. And the only thing which changes when we calculate the derivative of the activation function now is actually the fact that the activation function is slightly different, but compared with the standard binary case, the only difference is that we had a 1 instead of a Kronecker delta in this expression for the derivative. Now, when we are setting up the network now, we are going to have the output layer defined by the activation function given by the softmax function, whereas in the hidden layer, we are going to use the logistic function, the sigmoid function, as an activation function. In the code which I sent you, you will see that there is the possibility to use other types of activation functions. So when you're developing this code, and I just wanted to repeat some of the basic elements, what you need is obviously to collect and pre-process the data. This is often the more difficult part, in the sense that sometimes the data may come in different batches. There may be data which were collected in the 70s or in the 60s. People may use different units. And as I mentioned to you, I think it was last time, we had a student doing a master thesis, and it was after 1 month that she realized that data, so the weather forecasting, came in different units, depending on who measured it, what was the measuring station, and when it was done. So even the data was not uniform, and it took quite some time to realize why the model didn't fit well. So the need to define the model and the architecture. So this is the basics of the neural network. So if you go back to what we did in connection with the fitting of a polynomial. So the polynomial was our model in project number 1, but the neural network becomes now our model. So the architecture defines the model, which then depends on the type of activation functions which we're using. and the number of hidden layers, and the number of nodes or units or neurons which we have in every hidden layer. Then we need to choose the cost function and the optimizer. We train the model, we evaluate the performance on test data, and then we need to adjust hyperparameters. And these are the basic steps. So the data set which we are going to use is a trimmed down data set of the complete MNIST data set. And as I told you last week, this is simply done because else I would not have time enough in the lecture to run through the whole data set with 70,000 images with 28 times 28 pixels. So in this case, we have something like close to 1,800 images and 8 times 8 pixels. So the pictures are pretty blurred out. And we are going to set up a feature matrix or design matrix, which now has as dimensionality the number of inputs, which is going to be the number of images and the size of each image, which is 8 times 8, so that would be 64. Actually, 64 is going to be the number of features which we have. So every pixel here represents a feature. So you would now have a design matrix which has a dimensionality of roughly 1,800 times 64. Now you see quickly here that if you want to have a better image, this dimensionality quickly blows up. And that's why we often for imaging use what is called convolutional neural network, where we can filter out some features. And a typical example here is a very simplified case with the body mass index, where you would have one feature which is the height of the person and another one which is the weight, and that defines your design matrix. And then you have the 5 people whose height and weight we've measured, and that produces as targets the body mass index using formula. And then you could train a model where you want the model to reproduce this data, and then you could plug in height and weight of another person and see if the model is able to find the body mass index. So what we will begin with is simply to use this ready-made data set from scikit-learn. So scikit-learn has these data sets like the Wisconsin breast cancer data, the MNIST data set. We have tons of data sets which are included in scikit-learn and which allows us to read in the data without any problems. So as I mentioned, sometimes this can actually be the most time-consuming part. You may have a great algorithm for doing deep learning, but then converting the data set so that it is converted into a meaningful way can sometimes be something which really steals most of the time. So in this case, which we also went through last week, we simply run through it. We print out a simple example here. So you can see the quality of the data which you have here. And the label 8, you have to use an imagination to think that this is number 8. Number 7 here seems a little bit better. Number 3, perhaps one of them. And this is what you get when you trim down the data set to 8 times 8 pixels. But every number has a label, which means that we should then be able to train a model based on the numbers which we want to reproduce. And you see here, this is the number of inputs and the number of features. So this is our design matrix, which we're going to feed into the system. So this is the data. And then it's typical to split it in train and test data, as we did in project number 1. And here, again, we would use the functionality which follows scikit-learn. And you can write your own function if you want to. It's not that exciting. I normally recommend to use the functionality which you have in scikit-learn. So if we run through that one, then you will see now that we've split the data into number of training images and the number of test images. Then we need to define the model and the architecture. So you can use different types of activation functions. If you just have a single perceptron, then you would just have an input to the activation function, and that produces the output. And if you have a single perceptron model, you would simply have the different inputs, which are just weighted by a parameter here. And that is a much, much easier case. So that's a simple perceptron model where you don't have a hidden layer. By the way, if you're going to write a code for logistic regression and you have written a code for a neural network, logistic regression is nothing but a neural network without hidden layers. So if you just take the output layer, that gives you basically a code for doing logistic regression. It's not so difficult to see that. So you don't need to write your own logistic regression code. You can actually, if you have a neural network code, you can simply use that one to take away the hidden layers and then simply have a logistic regression code. And typically, we will be using an activation functions for the hidden layers, which is the sigmoid function. But in the code which I sent you, you will also find the hyperbolic tangent, rectified linear units, etc., etc. So the next thing we need to define is the number of layers. So we typically need to define the hidden layers, the number of neurons you want to have. So in this simple example, which we have here, I've just chosen to have one hidden layer, and then I have 50 neurons. So we have inputs 64, and then we have 50 neurons. So that gives us 3,200 weights to train. So even this kind of small case gives us a lot of parameters. And if you compare that to project number 1, where you had a polynomial fit, if you have a fifth order polynomial, if you take away the intercept, you would just have 5 parameters to train. And whereas here, we end up with already for this simple and very reduced case, we end up with a multidimensional surface where we want to find the optimal result for the cost function. And then we're going to have an output layer. So in addition to the weights, we have 50 nodes, which means that we have 50 biases. So in total, when we connect the input layer with the hidden layer, we have 3,250 parameters. Now, if we were to build a linear classifier, then we would just need a single neuron in the output layer, which then could output 0 or 1. You could use a Heaviside function, or you could use a sigmoid function again if you want to. And alternatively, like now, we are going to have a softmax case with the activation function for the output layer. And we're going to have 10 neurons in the output layer, each representing the possible numbers. And the activation function then is given by the softmax function. And in our case now, the different inputs are now going to the activation function, the z's. They are going to be moduled by the weights, which belong to a matrix, and then the weights, the biases b. And so for the output layer, since we have 50 nodes in the hidden layer, there are 50 outputs, and they connect with 10 nodes in the output layer. So we have 500 weights to the output layer. And in addition, we have 10 biases. So 510 plus 3,250, that's the number of parameters which we are going to train in the model here. So you see that this is something which grows quickly. And when we're going to build the neural network, what we are going to define then, and in this specific case, we are not writing this in an object-oriented way. It's very straightforward. We have the number of hidden neurons, the number of categories, which are 10. We now initialize the weights and the biases in the hidden layer by using a random number generator for the normal distribution. And then we simply set the hidden biases to just a small number in order to hinder, in case the weights are 0 or close to 0, that we stop the training. So we have an initial value here. And then we do the same thing with the weights and the biases in the output layer. And this is the way we would initialize and build our network. And these are the parameters we need to train. And then we do the feed forward pass, as we've been discussing in the lectures the previous week and the week before. So in the feed forward pass, we have different weights and biases for the hidden layer and the output layer. And so this L, uppercase L, is actually the input to the output layer. And then we have the final output, which is given by the softmax function. And then we end up, in principle, we end up with a matrix multiplications here. So we would have a weight matrix, which now has a number of inputs and a number of hidden nodes. And we are going to multiply the inputs with the weights. And we have now a input to the activation function, which now contains these matrices plus the biases. And in our case, then what we get is an output, which is then given as the input C to the activation function. And finally, we have a similar thing when we are looking at the output layer. So we have the output from the hidden layer, and then we have the weights and plus the biases. Actually, this should be a lowercase l here. So there's a typo here, which I didn't see before now, because this is actually the output from the hidden layer, which feeds into the input to the output layer. So this should be an A lowercase l. So I'm going to correct that one. And that means that the output is now simply given by this input, and then we have the softmax function. And here's how we would set up the feed-forward pass. So we have the sigmoid function for the hidden layer. We have the feed-forward part, where we now perform the matrix multiplication with the feature matrix or design matrix multiplied with the weights, plus the hidden biases. We calculate the output from the hidden layer, and this is now fed into the output function or the activation function for the output layer. And finally, we produce the final output according to the softmax function. And this returns these probabilities, and then we can make the final output. We define the probabilities in terms of the feed-forward pass, and this is just the prediction pass, which we are doing here now. And if you now look at what we had an image as an example. We're picking one of these images, which was labeled as number 8, and it was labeled as number 6, and we predict number 8. So what comes down here, just some technicalities, which I'm not going to go through here, because we've been discussing this many times. So when we are optimizing the cost function, it's a backpropagation algorithm. We would have a batch, a stochastic gradient descent with batches and epochs. So these are parameters which we need to fit and find the optimal ones. And we've been discussing the benefits, the pros and cons of using a stochastic gradient descent. So I'm not going to repeat that. The other thing which we can do is to add a regularization term, like we did with the Lasso ridge regression. So it's pretty common to add an extra term to the cost function, which is proportional to the size of the weights. And this is equivalent to constraining the size of the weights so that they do not grow out of control. And the typical regularization term is the L2, or alternatively, we could use an L1 regularization. And this is normally done only on the weights. So you see now, finally, the number of parameters which we end up with. So 3,250 weights in the hidden layer and 510 weights and biases in the output layer. And so that the gradient might actually be calculated for every parameter. And we use the backpropagation, which we have been discussing many times. And essentially what we end up doing is different types of matrix multiplications, which again, we have discussed earlier. So the implementation of this is now given by the code which you see here. I'm using a compact way to encode the different categories, the numbers, as bit strings. And this is the way I would typically label the different numbers. And then I perform a feed-forward pass here, where I now have the weighted sum of inputs to the hidden layer. And I perform the activation function. This is as before. This is the feed-forward pass. And then when I've done this, I have my backpropagation. And in the backpropagation, I need now to calculate the derivative of the cost function with respect to the outputs. And this gives me the probabilities minus the y value, which are the targets I want to reproduce. I get the error, which is then propagated back to the hidden layer. So this is the element which I need, this parameter delta, which I need in the backpropagation algorithm to calculate the gradients. And then I calculate the gradients and I find the gradients for the hidden layers. And with those quantities, I can actually start training the gradient descent method for updating the weights and the biases. So this is just the basic propagation where I find the gradients and for the hidden layers and for the output layers for the different parameters. So this function here just returns the different gradients. And then what you see here now is a code where I set up a given learning rate, a given hyperparameter lambda, and then I do 1,000 iterations and I perform my back propagation here. So if you look at this code, what you would see then is that the old accuracy on the data was 0.14, and then the new one is actually not impressive. It's 0.09. So this is not an accuracy which we would brag about. So what we need to do now, because what I did here was simply to fix a learning rate, 0.01, and similarly a parameter lambda. What is common then, and we are coming back to ways of doing this, is to train the network for many different learning rates. Now, in the network which you see here, I have done this in a very brute force way. I don't use any scheduler for the learning rate. So the learning rate is just kept fixed. And what I'm going to do then is to perform a grid search to find the optimal learning rates. And similarly, optimal regularization parameter. So I just set up a grid of values for the learning rates and for the regularization parameter. And next, we are going to implement these mini batches with a stochastic gradient descent. And that means that we will also have the number of epochs as a parameter. So you can now see the kind of object orientation here where we bake all these things in. So in this specific case, I could now have the X and Y data, the number of hidden neurons, categories, epochs, batch size. So these have become parameters of the model which we have. And then I'm setting up the weights and biases. I'm doing the feed-forward pass. I have the feed-forward output. And then I do the back propagation here. And this is essentially now the place where I train the output weights and the hidden weights and biases. So this will be the full back propagation piece. And essentially, this is the code for just one hidden layer here. I do the predictions. I predict the different probabilities for the output. And here I have my training part. So this has a loop over the number of epochs. And then I have a number of iterations which go through here. And then I just keep going till I reach a satisfactory output, which in my case is going to be the accuracy. And the accuracy simply counts the number of correctly classified outputs divided by the total number of observations which I have. So let's just rerun this one. And then we are now going to set up the number of epochs to 100, batch size to 100. These are just numbers. I call my function with the training data, the parameter zeta, the parameter lambda, which I have fixed. And then I have the number of epochs, etc., etc. And then I simply make my prediction here with those parameters for the values of lambda and the learning rate. So in this case, I was lucky because I already looked into the answers and I know which parameters lambda and for the learning rate, which give the best reproduction. And now we can adjust the hyperparameters here. And then when we do that, we simply run over this set of the values for the learning rate and set of values for the parameter lambda. So what I'm going to do now is just a plain grid search, nothing but that. There is nothing intelligent behind what I'm doing here, except I'm just running this for all the possible parameters which I have. And you can see the accuracy score when you have a learning rate which is very small, which means that you barely move, 10 to the minus 5, and you see that the accuracy is not impressive. And then you increase the learning rate, and then you see that the learning rate, the accuracy is actually increasing. So this accuracy score is one of the possible scores when we are setting up a classification problem. And now when I'm bringing up my, when I'm increasing the value of the learning rate, then you see that I'm getting an accuracy which is getting better and better. So humans, the typical score for humans on this data set with 1800 blurred images is something like 97, 98%. So if the network can do better than that, we are pretty happy, because then we are scoring better than a human. So this will just continue now, and sometimes I have a small overflow. Don't mind that. And this has now run through the setup. And one way to display the data is to use this package, which is called Seaborn, which allows us to plot the heat maps in a very nice way. And you can see now, if you look at the accuracy here, I'm just going to decrease the fonts a little bit. So let me just do that, so that I can squeeze in more place here. Okay. So what you see now is that when you have a learning rate which is 10 to the minus 5, which is this one, the accuracy is not impressive on the training data. But then when I have a learning rate which is 10 to the minus 3, I'm actually, or 10 to the minus 2 here, I'm actually getting a training accuracy which is 100%, which is pretty good. Even with this simple network which I built here with one hidden layer and 50 neurons. And then you see when I make the learning rate larger and larger, so 4 here stands to 10 to the minus 1, this stands for 1, and this stands for 10. You see that the accuracy score is pretty low. So lambda here goes from 10 to the minus 5 to 10 to the first, which means 10. And you see now that we have a set of parameters where we have a perfect training. And we would typically opt for this learning rate and for these hyperparameters lambda. And if you look at the test accuracy now, you can repeat the same calculations, and you see that my best score here is something like 96%, or between 95 and 96%. And I would say then that the learning rate of 10 to the minus 2 to 10 to the minus 3 is something which gives me a pretty decent accuracy. So in this case, I didn't do better than 96%. Now, there are lots of improvements which can be done to this very, very simple code. And one of these is actually us setting up the scheduler for the learning rate, where we can adaptively change the learning rate, like we discussed in connection with the stochastic gradient descents with the root mean square propagation, ADA-grad or ADAM, or any of these other methods. Now, you can also use scikit-learn if you're a little bit unsure about your own code. So scikit-learn has something which is called a multi-layer perceptron classifier. And if you want to do regression, you would simply specify that as a regressor. And in this specific case, you specify the activation function, the number of hidden layers, and then you specify the number of learning rates and the, actually this is the same, you feed in the learning rate and the number of, and the number of epochs. And then you fit, and then you make a prediction on this one by using the score functionality. So this is actually much easier than writing your own code, and it serves as a nice test. And if I just run through it, you will see that scikit-learn actually has implemented some of these methods which allow you to update the learning rate in a more intelligent way. So you would also see another thing here is that the number of iterations has been reached. So it has you would have to change the number of maximum iterations if you want to perform more iterations. So one iteration is one feed forward and one back propagation step. That's what is meant with iterations here. And if you look at the numbers here, you will see now that I'm getting actually something which is closer to 98%, which is the human accuracy. So this is not so bad. So I'm even getting close to 99% here, as you can see, with a learning rate of 10 to the minus 3 and a lambda value of 10 to the minus 2 here. So this is actually not bad. So this is on the training. And then we are getting closer and closer to 1. And then we can do the same thing when we do on the test set. And you can see here this accuracy score on the test set. And then finally, we can visualize everything. So if we do that, you will find something like this. So the training here is actually much better than my own code. And in this case, for learning rate of 10 to the minus 3 and 10 to the minus 2, I have essentially a perfect training for almost all values of lambda. And then I can do the same with the test data. And you see now that I'm getting close to a score of 100%. So I have a test accuracy, which is 99%, which is better than a human, which is around 97, 98%. Actually, I did much better, much worse when I looked at the data. I had serious problems in recognizing some of the numbers. So my accuracy score was actually much worse than what you see here. I didn't go through all the 1800 data points, by the way. Now, one thing you can do, if you want to, you can test the XOR and OR and AND gates, as we did earlier, but we are not going to do that here. I leave that as a small exercise for you guys. So this is just another data set where we are looking at the output from these different gates. And when you run it, you will see that it does perfectly well on the XOR and on the OR and the AND gates. And you may remember that when we tested this with logistic regression or linear regression, we failed miserably for the XOR gate. So this is just a way of setting it up. And I'm not gonna run through that. You can play around with it. The thing which I wanted to discuss a little bit more now is the way you can set this up with TensorFlow and Keras. So TensorFlow is actually an open source library, which was developed by Google and made public in 2015. And it's a computational framework, which allows you to build different deep learning algorithms. And it is actually specialized on various deep learning algorithms. And it links well with scikit-learn. So you can use scikit-learn to set up the data sets. And you can use the X-train, train and split functionalities. You can use cross-validation from scikit-learn, et cetera, together with TensorFlow. So these two libraries together, or alternatively, if you don't want to use TensorFlow, you have PyTorch, which you can use. So typically here, you would use pip install. You can use conda and install TensorFlow. Sometimes you may run into problems if you, depending on the architecture you have for your laptops. With the M1 processor, for those of you who have Macs, this was a hassle in the beginning because TensorFlow didn't collaborate. And to install Keras, you would simply do conda install Keras if you want to. So if you now look at the data sets which we have, we can now collect and pre-process the data for the MNIST data. And when we are going to build a neural network now with the TensorFlow, so you will see the way we would import TensorFlow here is simply to import TensorFlow as TF, is a typical way of doing that. I'm importing the same data sets as before, nothing different. And with Keras, it's very easy to set up the data. So I would now simply define the input structure. This is a sequential network. It's a dense network. I can specify the type of optimizers I want to use, the kind of regularization method. And then finally, when I look at the output, this is a categorical one, which means that I'm using the cross entropy, and I want to have more than just one class. And the labels, so this is a so-called one-hot representation of labels, which you can use. This is actually a functionality which is baked in TensorFlow. So you don't need to do the encoding yourself. And here I use the standard train test split functionality, which I have from scikit-learn. Now, the way you would now create a neural network with Keras is actually pretty easy. You obviously need to define the number of epochs, number of batches. These are parameters. And the typical parameter which you would tune first is actually the learning rate and the hyperparameter lambda. So the results are normally much more sensitive to those. So if you're a little bit in doubt whether you should, how many epochs and batch sizes you should use, I would normally recommend to use a standard gradient descent, which will be slow, and then find the optimal learning rates and epochs, and then do a better training, learning rates and regularization parameters. And when you found the optimal learning rates and hyperparameters lambda, then you can play around with these other parameters. Here, I have the number of neuron layers, the number of neurons in layer 2. So I have 2 layers. You can play around with these. I have the number of categories, which is fixed. I have only 10 categories. And the way you would now create your neural network, so this is a function which I'm setting up. I have a sequential model. This is a feed-forward stage. I add 1 dense layer. I have an activation function, which is just a sigmoid. And my regularizers is just an L2. Similarly, I have the next layer, which also has the sigmoid. And then I have my output layer, which now contains all the categories, which are 10. And then the activation is the softmax. So this is a very easy way by which you can build up a neural network using Keras. So you can alternatively write everything with TensorFlow. So TensorFlow becomes like a kind of library with its own Python definitions of arrays and matrices and so forth. So you could actually write the same code which I wrote in the beginning here with TensorFlow, but I normally recommend using Keras because that gives us a much more efficient way to implement all these kind of pretty nitty details. And here I would now just run through my training. I have defined all these functions. I run through the training. I define the number of epochs. And now I'm going to run my network. So I'm going to run the network here. And now it's just gonna, you just have to wait a little bit. And then it's going to take a little bit more time because now I made my network denser. I have a network which contains 2 hidden layers. So training is going to take more time. And normally I would actually recommend to use Google's interface for running these kind of neural networks, because then you would also have access to GPUs. Alternatively, University of Oslo has a set of machine learning nodes which you can apply for time. And you just search machine learning nodes, University of Oslo, and that will direct you to the application form immediately. So this is taking a little bit more time. And while this is running, this is actually where it fits to take a small break because we are at the hour now. So let me just pause the recording. So before the break, one of the things which we did was to set up this neural network using Keras. And Keras allows us to really set up a neural network in a pretty easy way. So we simply need to define the type of architecture, as you can see here. We have the sequential model. We have a dense layer, which we can use to define from 1 to many hidden layers. We can define the optimizers, the regularizers, and then clearly also the type of output, which is a categorical one, which we want to use here. And the typical way we would set up this layer, so this 2 categorical is a very useful functionality here. So there's a utility which is in Keras, and that simply allows us to transform the data. So we would import the data from scikit-learn, which prepares everything in a very nice way. So we don't need the hassle with transforming the data ourselves. And then it just gives the labels to the different numbers by converting them into a string of bits. So in this case, we have 10 numbers, and that means that we need 10 bits. That's one very simple way to encode the information. And then we have the structure of the network, which then contains the different layers, the type of activation functions we want to use, etc., etc. And you can also see here when we look at the optimizers, then we are using a stochastic gradient descent here, a plain stochastic gradient descent with a given number of epochs and batches. So there is no additional scheduler for the learning rates like ADAM or ADA-grad or RMS-PROP or any other variants of these. And then the metrics is now given in terms of the accuracy. We have the loss function, which is defined as the categorical cross entropy. And that simply takes into account that we have categories, and it calculates a cross entropy for that. So everything is, in a way, fed in. The way we set up the architecture is very easy. So you can have the overarching view on the way you set up the model. And then you will simply specify the features of the model in terms of the number of layers, neurons, etc., etc. And then you will define also the type of optimizers and activation functions through these definitions which you have here. So it gives you a lot of flexibility. And that kind of flexibility is also baked into the function which I sent you before the break. So everybody should have gotten that one. And when we are going to make our first neural network code, you can use these codes as a kind of sample. I'm, by the way, going to put online project number 2 next week, so we can discuss that one as well. And as always, you should feel free to modify it in directions you're interested in. And then you can see now it took a little bit more time, and now it's gone through all the data. And if we now visualize it, so Seaborn is this package which is very nice at making heat maps. I use it quite a lot. And when we now look at the data and plot them, so one of the things you're going to see is that with 2 hidden layers, the results are not that impressive compared to the results which we got with a simple feed-forward neural network using scikit-learn. So if we just let this run through here, and then so just resetting all the results to be plugged into the heat map figure. So let's just wait some few moments.
Morten?
Yeah, tell me.
To use the GPU with TensorFlow, is it set by default, or you have to? I mean, if you have a GPU, is default or?
No, it depends on the version of TensorFlow which you set up. So you have to set up the one with the GPU version. So you have a plain one which comes with the standard CPUs, but then you have to install the GPU version. Now, if you use Google's Colab, that allows you to use GPUs automatically. But if you want to do that yourself, you really have to set it up. So again, if you think back to the multi-layer network, so if we just go back and look at what we did with the scikit-learn, you see we actually did better with just one hidden layer. And if we now go down and look at the results which we had with using TensorFlow and Keras and 2 hidden layers, you see now that we are getting an area with the learning rate and the hyperparameter lambda, which is a little bit smaller. And if we look now at the final test accuracy, you see we don't reach a test accuracy beyond 98%. Whereas with the simple model, which we had with 1 hidden layer and 50 neurons, we actually got a better result. Now, I'm bringing this up because it's not given that you will get better results the deeper you make the network. So you can easily enter regions of overfitting, for instance, and sometimes it may be even more difficult to find the minima within a given set of iterations. So this is a kind of example of Occam's razors, where we often are looking after the simplest possible model to explain the data. So training with machine learning is something which is done by trial and error, in the sense that you have to try around with different number of hidden layers, different number of neurons in the hidden layers, different activation functions, etc., etc. So the only thing which the universal approximation theorem says, and we discussed that last week and the week before, is that what the neural network guarantees is that you will find an approximation to a continuous function to a given error. But it doesn't say anything about the architecture of the network, whether you need 2 hidden layers, 3 hidden layers, how many neurons you need to have in 1 hidden layers, many hidden layers, etc., etc. So these are things which actually not given a priori before you start doing the calculations. So there's a lot of trial and error when you run calculations for neural networks. And this is a clear demonstration that you would think that now I'm using Keras, I'm adding more layers, I should get better results, but that's not given. So you can do a similar bias variance trade-off with a neural network, where you could now play around with the architecture of the model, which then would be defined typically by the number of hidden layers, the number of neurons you have, etc., etc. And you would see the same kind of pattern with a bias which starts to increase and a variance which starts to increase, or a bias which flattens out and variance which increases. So the region for overfitting, or the overfitting problem, is something which will always be there. Any questions so far about the usage of these softwares? So Keras with the TensorFlow is very popular, and it takes away a lot of this hassle of actually setting up the networks and using all these different options. Now, if you go back to the code which I sent you, so I wanted to discuss that briefly, and I leave it to you, and when we're going to start working on project 2, to actually take a closer look at the gritty-nitty details. So in this code, what you will find are the basic features of the gradient descent methods, which we discussed before the winter break. So we can have a constant learning rate. We can add momentum to the gradient descent, which doesn't have anything with the learning rate, but it's a way to speed up the gradient descent, since we keep a memory of previous iterations. And then we have AdaGrad with momentum. We have RMS prop, and we have the Adam schedulers. So these are all examples of ways which you can include in a kind of more general code. So in this case, I also include AutoGrad in order to calculate the derivatives of the cost function and getting the gradients. And in this case, I can define different types of ways of updating the learning rates and also doing the gradient descent. So remember that the momentum doesn't affect your learning rate. Here we have just a constant learning rate. We have, so this means simply we return the learning rate times the gradient. We have momentum, which is added to the update of the gradients. And then we have the different ways to update the learning rate. So one is AdaGrad, the other one is AdaGrad with momentum, which we also discussed before the winter break. We have root mean square propagation. You can add momentum update here as well if you want to. So there's a lot of flexibility here. And here we have Adam. And the different models have also different parameters. Like we have this parameter for the Adam, which is called rho and rho2, which we also discussed, before the winter break. And what you would need then, if you want to initialize a scheduler, you simply create the object and pass in the necessary parameters, such as learning rate and momentum, as you can see here, right? So you have this momentum parameter 0.9. So this is a way by which we keep track of new and previous iterations. And you can feed in the learning rate. And same with Adam, you have to specify these parameters, and the values which are set here are those which people seem to agree upon are the best possible variables. And what you see here is a small example for how a segment of code which is using these schedulers could look like. And this code works for any of these schedulers. Then you simply have to define the one you want to use. So what I'm doing here is actually to make something which is pretty close to what TensorFlow is doing with Keras, so that you can play around with these different schedulers. Then the next thing is different types of cost functions. And here you should feel free to add more cost functions. So this contains the standard one for ordinary least squares, which is the mean squared error, a log reg cost function, which can be used in some cases. And then we had this cross entropy, and that takes in the target values here. The cost functions, there are examples on how to use it. Yeah, tell me.
Can I ask you about the functions you have shown right now?
Yeah, go ahead. Go ahead.
It's a question I have about Python, because you have a function with target that is the input, but inside you have another function.
Yeah.
How do you call the, I mean, do you, I don't understand at all. How do you call the, for example, the cost cross entropy? Or
okay, so what you're saying, which other function were you thinking of?
I mean, because, for example, to invoke cost cross entropy, you need to send the target.
Yeah, yeah.
But then the x, how do you send the parameter?
Okay, so if you look at what I have here, so you would now take, if you look at this cost function, I take the cross entropy, and then I'm taking the cost function. Let me see now. I should have a here I'm just calculating the derivative. So there should be a. So if you now look at I define, like here, the cost function to be the cross entropy. So I have a target array here, right? So this is the input, and I define that to be A, and then this NP array of this T here, right? Like this. So I've defined the array, and this is fed into this cost function derivative. And that means the cost function derivative just gets the name of the cost function, which is the cost cross entropy, and it takes this parameter A here, which is specified here. So this is just a simple array of data. And I have defined so that's the value X, which is plugged in. And then the target here is a global variable, which is this one.
Okay.
So that's a global variable. Just keep that in mind.
Okay. There was my question.
Yeah.
Because you cannot send it to the function. Okay.
Yeah. You can define it so that you can send it if you want to.
Yeah, but I mean, how do you have it defined? You can, I mean, you should add it to the definition.
Yeah. Oh yeah. So this is just done in the simplest possible way. So you have a global value, which is a target. So normally you're recommended not to have global variables, but in this case, I just made a global variable of the target, since that is going to be used by many functions. And the thing is, so about global variables, if I have something which doesn't change throughout the calculations, then I normally like to define that as a global variable. Does that make sense?
Thank you.
Yeah. So that's the
yeah, completely.
Yeah, because the target and the inputs when you're dealing with these supervised learning methods, I mean, they never change. And then it makes sense to define them as global variables. And that means that when you look at and this is a kind of other philosophy when you think of writing clean code, is that you want to avoid to transfer too many variables to a function. So I typically transfer just 1 or 2 variables at most to a function. So these are just ways by using AutoGrad as well, which I highly recommend. I'm getting lazy with age. So just to calculate all these derivatives, this gives you also more flexibility, because sometimes when you have a more complicated function, it's easy to make errors when you calculate the derivatives. You can have the correct equation, the analytical one, by paper and pencil, but then it can be easy to actually make errors when you translate that one into a code. So these are examples on how you use the cost functions. And then you can do the same thing with the activation functions. So you can define a class of activation functions and set up their derivatives as well. So you can have a ReLO, the linear, or the linear ReLO, just the rectified linear units, and then many other these functions. So you can actually, you should feel free. And as you know, there are tons of these different activation functions. And you should feel free to add more here, like the hyperbolic tangent, etc., etc. The exponential ReLO. So this is just an example on how you can structure the activation functions. And like here, we also have the softmax, which we discussed in connection with that, a simple, straightforward implementation of a neural network. And here you can see the typical usage of activation functions. Here just an array Z, and that is plugged into the activation function. It returns an output. And then you can also set up the derivative of the activation functions and calculate the value at this specific value C as input to the activation function. And these are just examples on the derivative of the sigmoid function value at this variable C, which we put to 4, 5, 6, and then you can compare that with the paper and pencil calculations. So then what comes next is actually the way you can set up a neural network. And in this specific case, there are ways we initialize it. We define the hidden functions, the output functions. We define the cost functions, etc., etc. The dimensions, the hidden functions, output functions, cost functions, etc., etc. So we've gone through these things. Here you define the number of batches, the number of epochs, the hyperparameters lambda, and then you define the way, all the kind of different options you want to set up. And you can continue like this. And this is a program which is pretty flexible, and it allows you to set up more than just one hidden layer. And you can see there's a feed-forward path, and there's a back-propagation path. You can define schedulers, compute the performance metrics, and so on and so on. So I invite you to take a look at these codes, because I was thinking that project number 2, a useful thing to do is actually to write our own neural network code. And this would be a more, how to say, I wouldn't say professional, but perhaps a better way of setting up a code for a neural network, which then gives you much more flexibility and gives you perhaps the same kind of flexibility which you saw when you were dealing with TensorFlow. So if we go back here, with TensorFlow and Keras, you can actually easily set up the neural network. As we saw here, you would simply define the number of hidden layers and the final layer, the output layer, and these just follow in a sequential way. And then here you specify optimizers, the type of activation function at the end. So normally when you do a regression case, you don't have any activation function. You would simply output what comes out. Any questions so far? So the thing which I wanted to end is more about the, there's a lot of blah, blah here, but I wanted to point out some of these. So we've already been discussing things like the activation functions and vanishing gradients. We've been discussing gradient methods, and the code which I sent you contains an implementation of that. So we don't need to go through this. The approximation theorems are things which we mentioned earlier. And the neural network simply guarantees that there is a specific error with at least one hidden layer. We can approximate any continuous function. Now, there are many pros and cons, and I just wanted to highlight some of them. So the neural networks They have their pros and cons, obviously, as every method. And as you probably have seen now, there are many parameters to tweak. And sometimes you can even hear statements like, I went to a seminar once and people said that we use just a plain gradient descent to optimize the parameters. And that worked better than stochastic gradient descent, but we don't know why. So we took what gave the best reproduction of the data. So you can use any type of topology, but you should start with the simplest possible one. Start with one hidden layer. And then something like 50 neurons, you can increase to 100, and then you can see how the network behaves. And then if you are not happy with the result, you can increase the complexity and make it deeper and deeper. But then you reach a point where you can end into the regional overfitting, and you will typically see that with an increasing variance. So the model parameters now are given by the number of hidden layers, the number of neurons, and obviously the activation functions which are using. Now the question is, which kind of hyperparameters should I tune first? So experience tells us that the hyperparameters to which the results are most sensitive are the learning rate and the hyperparameter lambda. And what many people do is actually they use grid search with cross-validation to find the right hyperparameters. So that would be the kind of validation approach which is included with the training part. So since there are many hyperparameters tuned, and since training a neural network on large data set takes a lot of time, you will only be able to explore a tiny part of the hyperparameter space. And typically as a guidance, the hyperparameters which are most sensitive are those which I mentioned. You can use a randomized search. And we do also have a tool which has the name of one of the people attending this course. So there's a tool which is called OSCAR, which implements more complex algorithms to help you find a good set of hyperparameters. So there are tools which have been developed, and this is ongoing research. For many problems, you can just start with 1 or 2 hidden layers, and that will work just fine. And as you saw for the MNIST data, we actually, with a simple multi-perceptron model with 1 hidden layer, we got a 99% accuracy, which is actually beyond what's normally seen as the human score on the same data set. For more complex problems, you can gradually ramp up the number of hidden layers until you start overfitting the training set. And more complex tasks, such as large image classification or speech recognition, they typically require networks with dozens of layers. And they need a huge amount of training data. So the thing then, and this is very useful, is that you will seldom have to retrain such networks from scratch because they're pre-trained networks. Like ImageNet has something like millions of images which have been pre-trained. And that helps. So if you have a network which has been pre-trained on images of animals, you can then feed in an image of let's say a dog, and use ImageNet and use that as a pre-trained neural network to train on images of dogs. So suppose you have 1,000 images of dogs, then you could use, let's say, ImageNet to train these images of dogs which you have. Alternatively, if you don't have pre-trained networks, you can actually train your own networks. And this is something which is not unlikely for some of you in your thesis projects. So how would you proceed if you don't have data? Now, suppose that you believe in some of the basic theory which has been developed for the kind of systems which you're studying. So this could be a simulation of how the brain is functioning. You may have some theoretical models which you can use to generate data. So I've been doing that for instance, in recognizing decay patterns from experiments, nuclear physics experiments, where we have specific decay patterns which we think theory reproduces well. So I can pre-train a network on theoretical simulations. Sometimes what you would end up with is to have a pre-trained data set which contains experimental observations, and in the case you're lacking data, you can add simulations to the data which are missing. Because keep in mind that for many of these complex tasks, these networks are extremely data greedy. So that's one of the drawbacks of neural networks, is that they need a lot of data to train well. So just keep that in mind when you're going to use neural networks or any of the deep learning methods, which are so-called supervised methods. This applies also to some of the unsupervised methods. So all these methods are data greedy ones. The more data you have, the better it is. Now, the thing which is nice with the theoretical simulations is that they often allow you to simulate a lot of data. And if you believe that these simulations give a decent reproduction of experiment, that can give you a pre-trained network which can work well on your data set. So this is something to think of, because I know that many of you will do something like this in your thesis. So if you have a partial differential equation solver which generates data on turbulence, for instance, and you want to use machine learning to simulate turbulence, then you could actually use theoretical simulations from the Navier-Stokes equations. Then we have the whole problem, as you have seen last week and the weeks before, the debate about activation functions. So we want an activation function which is simple. We don't waste too many cycles on calculating it. We want a derivative which is simple, which has analytical expressions, and which is easy to calculate also numerically. So there are many such pros and cons in the setup of the activation functions as well. And the activation functions are delicate functions because they enter the calculations of the gradients. And when they enter, if you think of the sigmoid, as we discussed last time, the sigmoid function has when the input argument goes to minus infinity or plus infinity, it has basically a slope which is 0. So it looks like Denmark seen from the sea. Actually, Denmark has a coastline. Maybe it's better to say the Netherlands seen from the sea. No, actually the Netherlands. You can't see the Netherlands because that's below sea level. Perhaps that's the reason why the Dutch people are the tallest people in the world. Because to survive, you had to raise above sea level. Sorry for this kind of jokes. These are kind of lame jokes, which I always crack. But anyway, your gradients become very, very, your functions become very, very flat. And like the sigmoid is one of these cases. And that gives rise to what's called vanishing gradients. And when you have vanishing gradients, the network simply stops training. And that's something which is, as you understand, is an unwanted feature. And there are lots of techniques to improve this vanishing gradient problem. Let me just take off this email reader because that's pinging in the background here. Okay, so the gradients then have also the problem that they can explode. And one of the things which we're coming back to when we are going to discuss a recurrent neural network is that of exploding gradients. And then there's a technique which is called gradient clipping. So there's a lot of this kind of hand tuning. So gradient clipping means simply that if the gradient exceeds a specific value, you just put it back to a small value. So it doesn't sound very, how to say, appealing from a mathematical point of view. But there are lots of these kind of tricks of the trade in deep learning. And if you go into the textbook by Goodfellow, Benjo, and Coville, you will see in chapters 11 and 12 that there are several sections on different tricks on how you can do grid search, avoid vanishing gradients, exploding gradients, etc., etc. So the field of deep learning was actually a field which never took off before a fundamental paper by actually Joshua Benjo and Xavier Glorot. where they discussed the difficulty of training deep feed-forward neural networks. And one of the problems was actually that everybody was using the sigmoid function. So when they replaced the sigmoid function with other activation functions, then one could actually train with much more flexibility different neural networks. So I invite you to take a look at that paper. It's actually a very good paper. And it's also discussed in a textbook, which we use. I mean, the textbook by Benjo and Goodwill, etc. And so I'm just going to leave this to you guys. So we have the ReLU activation function, and one of the functions which I didn't include in that code is the so-called exponential linear unit, which is also much used. So these activation functions, they become parameters in your theory or in your model. And people typically train neural networks with different activation functions. And then they try to figure out which one is the best for the data sets which we have. And there is no a priori favorite activation function, except that people tend to try to avoid using the sigmoid function, because the sigmoid function can lead to vanishing gradients when you have large input values. If you know that the input values are going to be small throughout the calculation, then the sigmoid function is okay. So in many cases, you can use the ReLU function in the hidden layers. It is a bit faster to compute than other activation functions, and the gradient descent optimization does in general not get stuck. So this is a kind of experience from calculations. And the ReLU function, coming back to this about the cost analysis, the ReLU function requires much less floating point operations than the other functions. And it has an extremely simple derivative. So that's also one of the reasons why people use the ReLU function. And for the output layer, for classification, then the softmax function is generally a good choice. And when you do the regression, it's common to not have any activation functions at all. You just output what the network gives you. There are many ways to deal with the exploding and vanishing gradients. So one is called batch normalization. And that technique consists of adding an operation in the model just before the activation function of each layer, simply by zero centering and normalizing the inputs, and then scaling and shifting the result using 2 new parameters per layer. So you add parameters. So all these methods, which you see here, they include some additional hyperparameters. Like gradient clipping, you have to decide when you want to bring the gradient back to a previous value. There is something which is called dropout, and that introduces a hyperparameter where you actually drop some of the neurons. So this is it's a fairly simple algorithm. So at every training step, every neuron, including the input neuron, but excluding the output neurons, has a probability P of being temporarily dropped out, meaning it will be entirely ignored during the training process, but it may be active during the next step. So that means that typically you would set this hyperparameter so that you skip 50% of the neurons. That's a way to also reduce the number of cycles. This is actually seen as one of the more popular schemes. It saves a lot of cycles because you would typically train only 50% in every stage. Then we have gradient clipping. And this simply means that you clip the gradients during back propagation so that they never exceed some threshold value. And this is very much used in recurrent neural networks, because in a recurrent neural networks, as we will see in 2 weeks, roughly, is one of these methods where the gradients really can explode because you're simply multiplying results from one layer at one time step with layers from a previous time step, and this can really accumulate and explode. So what batch normalization is actually the technique which is often most used. There are some links here of which you can find useful. And when we now take a top-down perspective on neural networks, the first thing is obviously to divide the data into 2 or 3 parts: training set, eventually a validation, or normally it's called a development set, where you actually find from the training set the optimal hyperparameters. And then you have the test set, which is just kept in a vault and never touched. And that's the one where you implement your best model to make predictions. So it's important that you never use the test data to train the algorithm. Actually, you will be surprised to see how many people actually do that. And that's a kind of cardinal sin. So the test set, you should think of that something you put in a vault. And this is done because sometimes it's very difficult to generate new data. If you have a medical survey of cancer patients for 30 years, it's very unlikely that you're going to run a new one for the next 30 years. So the data you have is what you have. On the other hand, if you're able to make simulations, like you often have in physics experiments or chemistry experiments, you have reliable simulations. You can actually use simulations to add more data, or you could use simulations to produce new test sets. So you could take the whole data set and train on that, make a model, and then you could produce new data. Or if the experiment is easy to run, then you can easily just rerun a new experiment and say that this is my test set. Now, if you're doing experiments, this is often not the best choice. But if you have simulations, then that's something which could be a useful part. The best thing now is to estimate the optimal error rate, like we did now, minimize underfitting, and make sure you're not overfitting. So these are the kind of three essential things if you take a top-down perspective. And if the validation and test set are drawn from the same distributions, then a good performance on the validation set should lead to similarly good performance on the test set. So, however, sometimes they may differ. They are collected using slightly different methods, or because it's cheaper to collect data in one way versus another one. In my field, nuclear physics, the training data for, let's say, proton-neutron scattering and proton-proton scattering is a world data which comes from many different laboratories. And some of the laboratories have a lower resolutions, they have a poorer detector. And that means that the quality of the data can actually vary across the world data itself. So these are things to keep in mind when you now are using a data set. How was the data set collected? Has this been run under the same conditions? If you're running a theoretical simulation, often life is much, much simpler, particularly if the simulation is easy to run. Like in project number 1, we just had a vanilla set of data, which was very easy to train and update. So if we now want to summarize this discussion of neural networks themselves, what we've seen is that these are data-greedy problems. A neural network becomes very difficult to train the larger the input. So if we have a realistic image with 200 times 200 pixels times 3 color channels, then your number of features really explodes, and your matrices start having huge dimensionalities. And that means that methods to reduce this dimensionality become very important. So you could think of everything which we are doing as a way to reduce the large dimensionalities of real-life problems. We need labeled data, and labeled data is something which is hard to obtain because often there's been a human which you have to pay to label your images. I could say that many of these, there was a very dubious project by the American Defense Department about classifying facial expressions with what you were thinking. So this is something which people were thinking of using in order to prevent, let's say, malicious actions by people. So one believed that the way your face looks like, your facial expression reflects what you're thinking. This is very dubious, and it has been refuted by the scientific community. However, what they did in this project was to train on images, on facial images. And the problem was that a facial expression has a cultural dependence. And most of these classifications were outsourced to poor countries because you pay people less. But then if you, across the world, I mean, a facial expression may have different meanings. So label data is often a big problem. And supervised neural networks are extremely data intensive, as we've been saying. It also works basically on homogeneous data. And if you want to look at heterogeneous data sets, then models like random forests, gradient boosted trees, etc., they perform much better. And many problems are actually not about predictions. And we often want to learn the underlying distribution. So that's where typically things like Bayesian machine learning kicks in. So there are many pros and cons. However, when we come to imaging, which is one of the success domains of deep learning methods, you will see that with convolutional neural networks, these methods have actually, they've actually proved to be so efficient that all other methods are almost seen as outdated. So when we meet again next week, we're going to look at the mathematics and the deep learning of convolutional neural networks, in particular with an emphasis on classification problems in image recognition. So this stops today's lecture. So I'm going to stop